of the requests that I made for you the other day when you got project number 4 was when you turn it over, I asked you to please write out your GCC student ID number polynomial for me to check by either today or Monday. Okay, so you're not going to have any My Math Lab homework for the week, and you're just going to have 4 problems that you're going to have most of class time today to work on. So please do this for Monday. I want to check it before you go on and do the rest of this, because if you mess up on the first part, the whole rest of your project is going to be not valid. Okay, so let's take a look at what this student polynomial looks like. The student polynomial, the first thing you notice is it's all in factored form. It has x minus n1, then it changes from subtraction to addition, and it just alternates signs all the way across. So suppose my student number was 0095237. Suppose that was my student number. This first 0 is n1. The second 0 is n2. The third digit 9 is n3. The fourth digit is n4. The fifth digit of my student number is n5. 1 is n6. 3 is n7. And finally, the last number of my student ID is n8. So all I do now to create my student number is I go up and I fill in each one of these spaces with the appropriate number. Does someone mind getting that door for me? So x plus 5, x minus 2, x plus 1, x minus 3, and x plus 7. So notice I start with a subtraction. My next one's addition, subtraction, addition, subtraction, addition, subtraction, addition. Now, if I wanted to simplify this, I could call these first 2 factors, which are just x, and the second factor, x take away 0 is x, x plus 0 is x, so I could combine that and just call that x squared if I'd like. So I get x squared times x minus 9 times x plus 5 times x minus 2 times x plus 1, x minus 3. Because I don't have any other digits in my number, no other digits are repeated here, right? I don't have any other 9s. I don't have any other 5s, 2s, 1s, 3s, or 7s. So the multiplicity on each of these factors is going to be 1. I have no other digits that's repeated other than my first 2 zeros. So please hand this in or have me check it off Monday before class starts at 20 of. Otherwise, I'll have to stay after with you to check. All right? It should be a pretty quick check. All right, so today we're going to continue our work with modeling, and we're going to be able to model now data that's much more complicated other than data that has a linear model. When we looked at models before, we were only focusing on linear regression. So today we're going to be taking a look at expanding our linear regression to include quadratic, cubic. And again, remember, linear falls under this umbrella of polynomial functions. So today we're going to be taking our polynomial functions and looking at polynomial regression. And again, this is supplemental. Caitlin and I put this information into the class. It's not in your textbook. So everything that you need to do this work, and if you could please not be working on your project right now, I'd appreciate it. What was I saying? We put this into the course. Modeling, we feel, is a really important part of applying what you're learning in this course to real world data. And so for an example, we've looked at using both GeoGebra and our calculators, which I'll supply for you today, or if you have your laptop with you, you might want to use GeoGebra to do some regression. So you might say, well, why do I need anything other than linear regression? Well, if you notice, I actually got this last semester. I got this data last semester because there was quite a bit of publicity in the local newspapers about heroin overdoses in Franklin County. And the governor of Vermont actually made it part of his state of the state address, and basically talked about the issues in the number of overdose deaths in Vermont, but not only Vermont, Massachusetts, including Franklin County. There's quite a bit of overdosing going on in the US, and it seems to have become this like epidemic almost at this point. And so I had two very close friends that lost their granddaughter and their niece to heroin overdoses in the last 2 years. I had one of my own family members, a nephew that lives out in Minnesota, die of a heroin overdose 3 years ago. And often this starts with accidents that people have, where they have injuries. Like my nephew was working for a public park service, and he fell out of a tree and really damaged his shoulder, and the doctor put him on, I never say this word right, oxycodone. And that is like great if you're in a lot of pain, but it's very addictive. And so that's what got him going into the whole cycle. And this is what they're finding, like a lot of doctors in Franklin County are trying not to prescribe people when they're in pain, so automatically give them this drug, because this is often the first step that leads people into this addiction. So, I mean, there's lots of reasons, there's a lot of societal reasons and all that that's going on with people, but it's become, as you can see, if you look at this graph, from like 2003 to where we are now, we've gone from under about 300 and say 80,000 deaths up to almost 700,000 deaths. So we as Franklin County, we have this opiate task force now that's working on this problem. We are going to try to get a rehabilitation center in Franklin County, because this is the sad part. A doctor sees someone, they're in trouble. If you can't get a bed somewhere within, the doctor that came and spoke at GCC last semester said within 48 hours, you're going to lose that person. And so the only other option you have right now, because there's no place in Franklin County for rehabilitation, is to literally have the person be put in jail to start their detox. So this is not a solution. So we have this huge opiate task force in Franklin County made up of lots of community members. The president of GCC is part of it, many of our local doctors. So if I gave you the points, like if we created a scatter plot right here, and I just gave you these points, try not to connect them right now, if you can, kind of erase that. So if I gave you the scatter plot right now, your only choice up to this point would be to try to fit the best line you could somehow through this data, so that perhaps you could minimize these vertical distances from the point to the line. That's the only models that we've looked at so far. Now that we've studied, oh, now I can use my pen. I'm so happy I can use my pen. Now that we've studied polynomial functions, we might be able to fit a curve, perhaps, that looks like this. Okay? Or maybe you might say, how about just a quadratic? But as you can see, with any curve, any polynomial curve, if you go too far outside your data set, like if we were trying to make predictions about 2014 or 2020, the higher your degree of your polynomial function, the quicker it rises and falls. So it's going to quickly run into model breakdown, and it's not going to be useful for us to do too much prediction outside of your data set. Does anybody know the word? I've used it before, but I don't know if I've ever written it down. When we try to make an estimation within our data range, we call that interpolation. Do you know, if I try to find the model for this data and say, how many heroin deaths will there be in 2014? So now I'm outside the data. Do you know what we call that process? Extrapolation, right? So when you're trying to predict or estimate outside of your data set or your data range, that's called extrapolation. You're going outside. Okay. And you've got to be really careful here with whatever model you're using, okay, when you start to extrapolate. Now, sometimes the model you have is great for the data set that you're presented with. And if you're looking at models that maybe do every decade and you want to go into years in between 2 decades, you're probably going to be, if your model is good, you'll probably get a pretty good estimate. But when you start to go outside in either direction, either years, the number of years greater than 2011, either into the future or into the past, which would be years prior to 2002, you've got to be very careful with your model. Okay, so that's just a little intro into polynomial regression. You will not see anything this complicated in the problems that I give you with this many twists and turns. So let's take a look at some data that I actually found. I try to sort of change this around every other semester or so just to get interesting data. Probably next year I'll start looking at marijuana usage because now with Colorado having it legal, is there any other state? Washington and Alaska, we're probably going to see real changes in the data set, an incredible rise. Unfortunately, it's going to look like it's just Colorado people, but the tourist industry has boomed since this change has been made. It was an interesting article I read in the Times over the summer about that. Okay, so here we see some data. And the data reflects the number of women in the full-time civilian labor force. So this excludes women who are in the military. And the unit here for the number of working women is given in millions of women. Okay, so you can see here that having it out to 3 decimal places is important because if I just rounded it to the nearest million, I'm excluding 851,000 women. 4.851 means 4,851,000. And even if I just rounded to the first decimal place here, I'm going to lose 51,000 people. So when your units are huge like this in the millions, the number of decimal places that you use will help your estimates to be a lot better models for predicting and estimating. Okay, so these are children, women in the workforce with children under the age of 6 years, and I've selected years. I got this from the U.S. Bureau of Labor Statistics. So I'm going to review for you the process of how we go through a regression. Everything is in your lecture notes, okay? The last page of your lecture notes before your homework says how to perform a polynomial regression. Now these directions were written for the TI-83 plus. And as you know, a lot of the calculators all the calculators I just bought for class are TI-84 pluses. I haven't been able to put an emulator yet on my smart board here. So I have just, while in between classes, I took some pictures of the screens with my iPhone and I put them onto our lecture for today. So I'll try to show you the difference. There's only one spot where the screen looks different than the 83 that you're going to see. Okay, so let's just recall what we do. First of all, we have to know what our 2 variables are. It says here, let's type the data into L1 and L2 and then create a scatter plot. We're going to let T equal the number of years since 1970. So that means we're going to just make a little change here to the year, which we're calling T. We're not going to enter 1975, 1980. We're actually going to just shift this data a little bit to the, which way are we going to be shifting it? Okay, to the right. And how are we going to do that? We're going to say let T be the number of years since 1970. So this first data point, my very first data point that I'm going to put into my L1 column in my calculator is not going to be 1975, but it's going to be what value? 5. And how'd you get that, Caitlin? Yep. So we've had good practice with this by now. This is often what we do when we're looking at data that involves years. So it's going to be 5, 10, 15, 20, 25, 30. So in my first column, I'm going to have 5 up to 30, And then in column L2, I'm going to actually enter the number of millions of women in the workforce. Okay. The other thing is to be clear what your independent variable is and what your dependent variable is. Time here is our independent variable that goes along our horizontal axis, and the number of women in the workforce is our dependent variable that goes on our vertical axis. So on our scatter plot, we'll have the year here since 1970, and on our y-axis we'll have the number of women, and our unit is in millions. Okay, so this is what the axes will look like for our scatter plot. So let's recall how we do this. So, and I know it's been a while since you've done it, but everything will be, like I said, it's all written out for you. So let's see how much you can remember. I'm going to clear everything here. Second quit. Got to clear everything out from my first class. Clear. Let's get all this cleared out. Oh boy, I got to clear everything here. Clear. Got to go up and turn my stat plots off. So if you get a calculator, you might, some of your previous class members of my first class may have not turned everything off for you. So that might be a great place to start when, so all your stat plots are off. The other thing, don't forget, is that in order to get your R value and R square value, you have to make sure your diagnostic is on. That's second catalog, which is the second 0. And you've got to go down, all the way down, keep going, keep going, keep going until it says diagnostic on. And I think because all the calculators were used in my first class, you won't have to worry about that. But diagnostic on, you hit enter, and then you have to hit enter again until you see the word done. Okay, now you know you're done. All right, so let's go into our stat button. We're going to edit our lists. And oh, isn't that nice? I have everything entered into each of these columns already. There's my L1 column and my L2 column. Okay. Now, if you want to clear your list, do not hit delete because you'll actually lose all of this entire column. If you want to clear a column, you just do clear, enter, and then that will wipe out all your data. Okay. So I've got all my data here. Now I want to perform a regression, but I need to look at my data to see what am I going to try to fit to that data. So let's go up to turn on stat plot, hit enter, put your plot on. Notice your scatter plot is always the first one highlighted. All your data is in L1 and L2. So the only thing you have to remember now before you look at the graph is to tell it to do zoom stat, zoom stat. So that's zoom 9 is zoom stat. And there's your scatter plot. So do you think you could fit a line to that data fairly reasonably? Yeah, let's try. Okay, so let's review how we fit a line here. So you hit stat. Now you go over to calculate. And this is all written down. You might want to follow along in your lecture notes. You go down to linear regression and you hit enter. And now with your TI-83 plus, you have to literally put in your two lists where your data is located. Where is your data located? It's located in L1, which is the little L1 is located right above your 1 button. So you hit second 1, there's your L1, you put a comma, and then L2 is right beside it, second L2, another comma. And now you have to say, where do you want to store this equation once I tell you what it is? Where do you want to store it? Well, if you recall, we wanted to store it in one of the y equals equations. We had y1, y2, y3, y4, y5. So in order to tell it to do that, you hit your vars button right here. And you scoot over to y vars because that's where you want to put it in the y variables. So you scoot over. Then you just hit enter, enter. So if you want to put it in y1, you hit enter right now because it's on y1. So let me tell you something. You're going to have 4 data sets that you're going to work on today. And what a lot of my students did in the first class is once they entered the data for this and put it in y1, then they went down to number 2 and they erased everything in y1. So if we went back to work on it, they didn't have the data anymore. So if you do everything for problem number 1 and put it in y1, when you go down to y2, go down to number 2 here, put that equation in y2. You can turn off the equation in y1. I'll show you how to do that in a second. You can also put the lists for this data in L3 and L4. There's nothing golden about L1 and L2. Okay, so you don't have to just use L1, L2 all the time in Y1, so that if I'm walking around the room and I get to you after you've already started your second set of data, I can go back and we can look at the first set together without you having to do it all over again. So I'm just going to hit Y1 here. And now when I hit enter, notice what I get. I get the form of linear regression. The equation's always going to be, I always use the hat, y hat. And why do I use that? Because it reminds me that I'm using a model and that this model isn't the exact data. It's fitted data. We're fitting the data based on the number of years we have after 1970, and we're predicting or estimating how many women are in the workforce. So what's my value for A here? A is acting just like my slope, because usually we see this when we work with straight lines as mx plus b, right? So A is 0.21107. How many places am I going to carry this out? Well, the more places I carry it out, the better, because remember, we're dealing with millions. It's all going to be in your data. It's all going to be stored in your calculator with all of this precision and accuracy. So for reporting it on your lecture notes today, you can just go out 3 or 4 places. It's not a big deal because it's in the calculator. So 0.211, and if I bring it out to 4 places, I'll make another one, and that's x. So remember, this is acting as my slope. This is also with my linear regression, that's also my leading coefficient. This is also my leading coefficient. It would have a sub 1 as its little subscript because the highest degree here is to the first power. And then my constant term here is b, which you're used to calling the y-intercept, 3.99. How many places did I go? 1, 2, 3, 4, 1, 9. Okay. Now, when you do a linear regression, we were using the correlation coefficient R before to see how good a fit it was. But R, remember, was a value between +1 and -1. And it told us how strong our linear relationship is. Well, if we're going to start now changing to curves, there's not going to be an R value for curves. There's not, because curves don't have linear strength. So the statistic that we look at to compare so we can figure out which of our models is the best is going to be called R square. And when you use it for linear regression, you use a little baby R square. And when you use it for any other polynomial other than a straight line, you use capital R square. So the R square value is going to be important because it's going to help us to be able to compare our models. So the R square value for this linear regression is 0.959. So this equals 0.959. So let's get a picture of this and see how well this line fits the data. So I'm going to do, I've stored my equation. There it is. It's in Y1. That's where I've stored it. So now I hit zoom 9. Not only will I see my scatter plot, but I'll see my straight line. So there you go. And as you can see, it's a pretty nice fit. So let's take a picture of this. And we'll scoot it right in here beside the R square value. Hey, it didn't make a sound. That's interesting. I have the recording on, right? Usually makes a sound. I hope I'm recording. Yep, I'm recording. All right. I don't know why it didn't make a sound. Did you notice I got a new pen? Works fantastic. So much better than the old one. Hopefully my writing will be better. Okay, so there's your linear model. And with this R square value, what that roughly says, R square is about 96% of the fluctuation. Sometimes people call it noise in the data. It's this kind of variance in between the actual data in your line can be talked about or predicted based on just knowing what year you're looking at. So it's a pretty tight fit. The rest of the variance or fluctuation, we don't know where that comes from. Okay, and that's what makes this not a perfect fit. There's something else going on here. Okay, so let's look at a regression with a parabola. So again, you take out your calculator. L1 and L2 is already entered, so it's not too much of a problem. But here's what you want to do. Notice your equation stored in Y1. So if you just want to take a peek at your parabola, turn Y1 off, and all you do is just place your cursor over the equal sign and hit enter. It just toggles it off, okay? You see how now Y1 is not on because it's not highlighted, all right? So let's do a quadratic regression. You go over to Calc, you go down to 5 now where it says quadratic regression. Now you still put in your L1, your L2, you still go over to vars, you say I want to put it in Y vars, enter, but now I want to put this equation in Y2 because I want to keep my straight line in there in case I want to compare both of them on the graph. So I just scoot down to Y2 and that's where I store it. And I hit enter and there's all my data. So here's your familiar ax squared plus bx plus c model. So this is what my quadratic regression looks like. Negative 0.00482 x squared plus b is 0.37992x plus my constant term is 2.8662. Notice my r squared value. Now it's a capital R square, and my r squared value is 0.986. Whew, that's a pretty tight fit. So if I were trying to choose between these two models, I would feel pretty confident with either one of them because my r squared value for my linear regression and my capital R squared value for my quadratic regression is quite high, quite strong, very strong, incredibly strong, wicked strong, all right? So I'd feel comfortable using either one of these models. But there is a difference in these models. Take a look at their graphs. Look at how close the, again, zoom 9, look at how close this parabola fits this data set. It's amazing to me that this is real world data. I did not make this up, and yet we can get a model this close to fitting that data. So what do you know from the leading coefficient here? What do you know about this parabola from looking at the leading coefficient? What's going to happen eventually as my end behavior, as my number of years go out way past 2000? What's going to happen to my number of women in the workforce? It's going to be going down, right? And eventually it's going to be negative women. So we know at some point this model's breaking down for us. Okay, what if I wanted to see where this model is going to estimate the maximum number of women in the workforce? Why did I say maximum, by the way, and not minimum? I just threw something at you real quick and I didn't even explain. Why did I use the word maximum number of women in the workforce? Why did I say that? Someone other than Caitlin? Nobody knows why I would use the term maximum? Looking at this parabola? It's an upside down parabola. Well, it opens downward, right? We know that the leading coefficient's negative. So our vertex is going to be a maximum. And so the maximum output here will be we're going to predict the year when the number of women reaches its all-time high, according to this model. All right, so let's take a picture of this. Oh, I keep remembering I got to put my camera up there. Keep forgetting, not remembering. So let's put a picture of this model over here. And oh, there's a sound. It came back. All right, so if I wanted to ask, when will there be the most number of women in the U.S.? When will there be the most number of women with children under the age of 6 in the U.S. workforce, civilian workforce, right? I can use, anytime you see most or highest or lowest or least, that tells you to look for the vertex. And how do you look for the vertex? Well, if you go here to your calculator, it's under calc up here. See these four letters in yellow, CALC. So you hit second trace, and it's going to be the maximum value. So you just scroll down to 4, you hit number 4, whatever you want to do. And now you get this left bound, right bound, and all that. And you know, without even seeing the full picture here, you can't go to the left and right. But the good thing is you don't have to worry about using your cursor to go to the left of where the maximum is at the right. You can just hit enter, enter again, and anytime you see the guess, you can hit enter. And there's your maximum. It gives you the coordinates for your maximum, 17.5, comma, 8.037. If your data continues to go up, yes. I know. Because this is a model. It's not the exact data. So it's predicting that 17 and a half years from when? When did we start this data set again? 19 what? 1970. So it's saying we've already reached our maximum. Yep.
What if, like, that was spot on the graph, the cursor wasn't?
It will still work for you. Okay. All right. So so let's see how we would use these models here that we have to make predictions. Oh, I want to show you what it's going to look like on the 84 calculator, since I did all this work between classes. So this is the screen on the calculator. On the 83, it comes up and it says quad regression, and you put in L1, L2. When you hit quad regression on your 84, these brand new calculators, this is what the screen looks like. It will already have L1 and L2 in there. So all you do is you scroll down to where it says store your regression equation. This is the only part that's different. The process to get your equation stored into Y1 or Y2 is exactly the same. You just cursor down to where it says store regression equation. You press your vars variable, you press your vars button. You scroll over to Y-vars, you press function, and you press Y1. And then it puts a little Y1 right here on the screen. And then to get your model and all your data, you just cursor down to where it says calculate, which is right here, and you hit enter. And this is what pops out. Your A, B, C value and your R-square value. Okay, so it looks different, just the screen is different. And all you have to remember to do is just cursor down a store regression equation. All the other information I have on your lecture notes is exactly the same. Okay, and I'll keep this up because a lot of you you'll forget when you get there. I'll keep this screen up. Yep, Katie?
Do you have somewhere?
Do I have somewhere? Yeah, it's in your project. Your project 2 is when you did it for linear regression. So instead of fitting a line, you'll be looking for the command that fits curves. I'll help you with that when we get there, okay? Yeah, I'll help you with the GeoGebra. Okay, so let's look at these two regression, the regression line and the regression parabola, and let's see how we can predict the number of women who'll be working with children under the age of 6 in 2011. Okay, so again, you've got to know what our first year is. Our first year is 1970. So what's going to be the value of X, or T in this case, either one, for 2011? How am I going to get that number to put into my model? It will be 41. How'd you get that, Andy?
70 plus.
So you did addition, or you could just take the data, 2011, and subtract 1970, and that gives you 41. Okay, so you're thinking, oh my God, do I have to go and do all this calculation here, like put my 41 in there and do all that? No, because your calculator will do it for you. Your calculator has these two equations stored in it already. Let the calculator do the work for you. That's why I said don't get rid of y1 and y2. Here are your two. I'm going to turn y1 back on now. I'm going to hit enter so that equal sign. y1's in your calculator and y2's in your calculator. What x value do you want it to calculate the number of women in the workforce for? 41. So go right here, second table set, and put in the number 41. 41. And then hit second table. And notice for the number 41, here's the prediction based on your linear model. There'll be 12.646 million women. Here's the prediction based on your quadratic model. That's actually, I think I did something wrong when I found the maximum value before. And I think it's because we didn't have the full parabola in there, like what you were saying, Katie, and what you mentioned, Isabella. So I think you have to have at least what looks like the maximum height in there, and you can then hit enter, enter, enter. Because look, this is already predicting a bigger value than that. So the calculator does it for you. So the linear model is going to predict that there'll be 12.646 million women in the workforce. And your parabolic model predicts 10.33 million. So let me take a little picture of that. And what I realized is someone in my first class said, well, do you know how many women there are in the workforce now, or 5 years ago or 10 years ago? And I said, no, that's a great question. And we have someone in our first class that works in the library. So I volunteered him. I don't know if he was happy about that. He may or may not do it. I don't know. But anyway, here's the data. And your confidence level should be pretty high for this. So if you're at all interested in seeing which of these models is a more accurate prediction based on the actual data, like for 2005 and 2010, you could go to the US Bureau of Labor Statistics and get this information, because that's where I got it. So that's pretty much it. Use the leading coefficient test to determine the end behavior to the right for each model. So as our time goes beyond 2000, what's the linear model going to predict? What's the end behavior for the linear model going to be? As time goes towards positive infinity, what's going to happen to the number of women in the workforce? It's going to go up. The linear model keeps going up. It's going to go towards infinity. There's not going to be any stopping it. What about the quadratic model? The quadratic, remember, has a leading coefficient that's negative. So we know it's like this. So as time moves along, what's going to happen to the number of women in the workforce? It's going towards negative infinity. So at some point, both of these models are going to stop being useful to us. Maybe they've already stopped being useful. I don't know, because I don't have the data for 2005 and 10. Okay. So that's sort of like the little baby lecture on this stuff. Most of it is you just got to kind of plug away and remember the keys and use your notes, and I'm here to help you, okay? And you have your table mates to help you. But any questions before we go on about any of this, Caitlin? I would just say my confidence level is very high because my R-square is very, very strong. I would feel very confident using either model, even though both of them give you very different numbers. At this point, I would probably use the quadratic, just because the R-square value is. Someone may argue, well, that's going to start going down. Well, you might say, do we know anything about the number of women in the civilian workforce? Are we expecting that since 2000? Well, think about this. From 2000 to 2010, we were in a war, several wars. So some women, there were probably a larger number in the military workforce from 2000 to 2008 or 9. Let's see, when did we leave Iraq? 2010, I guess, right? When 2 years after Obama became president, we withdrew from Iraq. So you might suspect that, what do you suspect the number is right now in the workforce? More women in the civilian workforce or less? You would think maybe more women. Okay, so who knows? Maybe the linear model is more accurate. Maybe the quadratic. All we know is just based on this data, the quadratic model is the best. And that's as far as we can go. Unless you know a little bit more and you think about your data in terms of the actual context. You do have a sense. You're not all that old or young, excuse me, you're not all that young that you don't have a sense of the last 5 or 7 years in terms of what's been happening in the US. So you might be able to say, well, I think I feel better with one of these models more than the other. So if you're thinking about selecting a model and you don't know whether you should use a linear or a quadratic, cubic, whatever, to model a situation, there's no hard and fast rule, folks. There's no hard and fast rule. It's really, you really have to look at the data, see which one of your functions fit it the best. You look at the R-square value, you look at the scatter plot. But if you have two that are really, really close, you want to pick the simplest model to work with. So if you had a choice between a cubic and something to the 7th power with this big long equation like this, and their R-square values were fairly close, use the cubic. Okay? The model should make sense within the context of the real world situation. Okay, so you got 4 data sets. You have a little more than a half an hour to start working on this. Let me know if you have any questions.